Next, I'm going to discuss another important concept called the convex Hall for a subset of Rn that is not necessarily convex. As we can see in this figure, this is a non-convex subset of Rn, and the smallest convex set that contains omega is called the convex Hall of omega, and it is actually the intersection of all convex sets that contains omega. Okay, so this is the definition. Let omega be a subset of Rn. The convex Hall of omega, denoted by co-omega, is the intersection of all convex sets in Rn that contains omega. That is, the convex Hall of omega is the intersection of all sets of C such that C is convex and omega is a subset of C. Okay, so from the definition, we have the following observation. From the definition, we see that the convex Hall of omega is the smallest convex set that contains omega. That means, first of all, the convex Hall of omega is convex. This fact is very obvious because we know that the intersection of any family of convex sets in Rn is also convex. So, by the definition, the convex Hall of omega is the intersection of all convex sets that contains omega. Therefore, this is a convex set in Rn. And the second part means that if omega is a subset of a subset of C1 and C1 is convex, then the convex Hall of omega is a subset of C1. So it tells us that omega is the smallest convex set that contains omega, and this also follows from the definition, because here C1 is a convex set that contains omega, so it belongs to this collection. This is the collection of all convex sets that contains omega, and the convex Hall of omega is the intersection of all such convex sets. Therefore, it is a subset A of C1. Okay, so these two facts are very important later. It follows from the definition that the convex Hall of omega is convex. Okay, this fact follows from a very important property of convex sets, that is, the intersection of a family of convex sets is convex. In this situation, by the definition, the convex Hall of omega is the intersection of all convex sets that contain omega. So it is the intersection of a family of convex sets. So the convex Hall of omega is convex. Okay. And the second observation is that the convex Hall of omega is the smallest convex set that contains omega in the following sense. If C is convex and C contains omega, then the convex Hall of omega is a subset of C. Okay, this also follows easily because if C is a convex set that contains omega, so it belongs to this collection. Okay, and the convex Hall is the intersection of the collection, so it is a subset of each set in this intersection, and in particular, it is a subset of C. So we're going to use these facts in the next proposition. Okay, so the next proposition gives an explicit representation for the convex Hall of a subset of Rn in terms of convex combinations of its elements. Okay, so suppose that here omega contains 3 points W1, W2, and W3 in Rn. Okay, so this is W1, W2, and W3. Okay, and as we can see that W1, W2, and W3 here are 3 points in Rn, so this set is non-convex. Okay, and then from this figure we see that this triangle is the convex Hall of omega. So this is the convex Hall of omega. And as we can also see from these figures, this triangle is the set of all convex combinations of W1, W2, and W3. Okay, therefore, the convex Hall of omega is equal to all convex combinations of W1, W2, and W3. Okay, so the convex Hall of omega here is equal to the collection of all convex combinations of elements of omega. And the situation works for any subset of Rn. Okay, here this is a finite set. It works for infinite sets as well. So let me go ahead and state the proposition and give the detailed proof. Let omega be a subset of Rn, then the convex Hall of omega is equal to the set of all convex combinations of omega, that is all elements of the form lambda I times Wi, where I runs from 1 to m. Over here, each lambda I is greater than or equal to 0. The sum of lambda I, where I runs from 1 to m, is equal to 1. each wi belongs to omega, and m here is any positive integer. Okay. Now I'm going to give the detailed proof of this proposition. So the idea is as follows. We're going to let C be the set on the right hand side of this representation. That is, C is the set of all convex combinations of elements of omega. Okay, we're going to show that C is convex and C contains omega. So then by this fact, the convex Hall of omega is a subset of C. Okay, and after that, we're gonna prove that C is also a subset of the convex Hall of omega, and we complete the proof. Okay. Let C be the set on the right hand side of the representation. The first observation is that C is convex. How come C is convex? We will use the definition of convexity of Z in order to show that C is convex. Okay, so we fix X and Y in C, and also lambda in the interval 0, 1. Okay, then by the definition of C, X is a convex combination of elements of omega. So X can be written as the sum of alpha I times AI, okay, where I runs from 1 to P. Here, each alpha I is greater than or equal to 0. The sum of alpha I, where I runs from 1 to P, is equal to 1. And also, each AI belongs to omega. Okay? And similarly, Y is also a convex combination of elements of omega. So it can be written as the sum of beta J, Bj, where J runs from 1 to Q. Here, each beta J is greater than or equal to 0. The sum of beta J, where J runs from 1 to Q, is equal to 1, and each Bj belongs to omega. Then lambda x plus 1 minus lambda y. So we multiply this by lambda, and we multiply this by 1 minus lambda. So we have this sum. The sum of lambda times alpha I, where I runs from 1 to P. Over here, we multiply by AI, okay? And then we add the sum where J runs from 1 to Q of 1 minus lambda times beta J times Bj. Okay. Okay. Now, if we set this by alpha, and if we set this by beta, we will see that the sum of alpha and beta is equal to 1. How come this is true? We can write over here. So we're going to see that the sum of all coefficients in this representation is equal to 1. Okay. Y, we look at the sum of lambda times alpha I, where I runs from 1 to p, and the sum of 1 minus lambda times, this is beta j, where j runs from 1 to q. This is equal to lambda times the sum of alpha I, where I runs from 1 to p, and 1 minus lambda times the sum of beta j, where j runs from 1 to q. Okay? And as we know, this is equal to 1, and this is equal to 1 as well. So this is equal to lambda plus 1 minus lambda. So it is equal to 1. Okay? Now, in this representation of lambda x plus 1 minus lambda y, we see that each element here is in omega. That is, alpha I is in omega for each I, and beta j is in omega for each j. And the sum of all coefficients is equal to 1. Okay? So lambda x plus 1 minus lambda y, by the definition, is a convex combination of elements of omega. Therefore, it belongs to C. So lambda x plus 1 minus lambda y is a convex combination of elements of omega, and hence lambda x plus 1 minus lambda y belongs to C, because C is the set of all convex combinations of elements of omega. So we have seen that if x and y are in C and lambda is in the interval 0, 1, then lambda x plus 1 minus lambda y is in C. Therefore, C is convex. Okay? The second observation is that C contains omega. This observation follows directly from the definition of C. So we fix any W in omega. Then we will show that W is in C. Then W can be written as 1 times W. So this is just a convex combination of one element of omega. So by the definition of the set C, this is in C. Okay. Now, from these two observations, C is a convex set, and C contains omega. As we saw earlier, the convex Hall of omega is the smallest convex set that contains omega. So from here, we have this conclusion. The convex Hall of omega is a subset of C. Okay? To finish the proof, I'm going to show that C is a subset of the convex Hall of omega. Okay? So fix any x in C. Then, by the definition of C, X is a convex combination of elements of omega. Okay. Then, because the convex Hall of omega always contains omega, we see that each Wi belongs to omega. So it also belongs to the convex hall of omega. Okay, and since the convex hall of omega is convex, by the previous proposition, the convex hall of omega contains all convex combinations of its elements. And we see here that each wi is in the convex hall of omega. So it follows directly that X here is a convex combination of elements of the convex hall of omega, which is a convex set. Therefore, it is in the convex hall of omega. So we see that the set C is a subset of the convex hall of omega. So we already proved that the convex hall of omega is a subset of C, and C is also a subset of the convex hall of omega, and therefore we have the equality that C is equal to the convex hall of omega.